Yo, so I've been gone for a minute, y'all. And to be honest, I just got like COVID and then I stopped making the videos and then I just kind of got burned out with school and everything. But it's all right. When you get burned out, you got to get back into it somehow, ease yourself back in. And so that's where we're at is we're going to ease ourselves back in to these videos. And specifically, I'm going to try to finish up chaos theory before my school starts again, or at least, make bigger of a dent in that. I didn't realize how tough these videos would be to actually make, but it's kind of a grind. And so, I'm going to hope to stick with it and continue to put out content for y'all. And with that being said, let's jump right into it. So this is a very nice math question. And basically asks, can a parabola of arc length 4 be inscribed in a circle of radius 1? All right. And I found this problem on a PUTNAM practice test, or it was like a previous PUTNAM from a few years ago, and it was an A6 question. So it was the toughest question on the PUTNAM, which is like a national math competition. Okay. And I was looking at it, I was like, this shouldn't be that hard. But weirdly enough, it's like a tough problem. Okay. And this problem actually illustrates to me um, some of the drawbacks of like Euclidean or like normal modes of calculus that we have. I think the normal ways of us doing calculus really kind of neglect certain geometries and favor others, right? So we very much favor like a more cubic um, and triangular geometry rather than one that's more spherical or elliptical. And so, because of that, sometimes problems like this, which seem simple on the surface, can be extremely difficult because we simply don't have the proper tools. Okay, and so let me just go get into what I mean. Okay, so solving this problem, well, the first thing that comes to mind is we need to use the arc length of the parabola, determine essentially a an arc length integral to calculate, you know, based on these points of intersection between the circle and the parabola. Well, let's integrate and find the arc length of the parabola and set it basically equal to 4 um, or less than 4. And so essentially, in order to do this, we first need to figure out, okay, where do I want to put the parabola if I'm trying to fit it into my circle? And the first logical kind of thought process that you have is like, all right, I'm going to put the parabola at the, symmetrically with the vertex at the base of the circle, right? That seems like the most efficient way to place the parabola in the circle. And it is. It is, in fact, the most efficient way. Okay. Um, and now, essentially, thinking about this problem, as we increase, like let's say we have a parabola of like alpha x squared minus 1, okay? And so if we start increasing this alpha, all right, and making it super super large, then we're going to asymptotically approach um, something that looks like this, okay? And the parabola inscribed within the circle is essentially going to be 2 diameters of this circle, and the circle has a diameter of 2. So we would expect that the arc length of this parabola should be approaching 4. Okay, but the question is, okay, so is this the most efficient way to fit in the parabola? Is basically squeezing it as far as we possibly can to try and get it to approach 2 diameters. Is that the most efficient way or not? And it's not so intuitively obvious, um, but let's just kind of attack it that way and see what we can do. So if we set up the parabola to be alpha x squared minus 1, okay, then we know that essentially the arc length of this parabola within the circle is going to be the integral from x star, negative x star to x star, where I'm going to set x star to essentially be the point of intersection with the circle, okay? And then we have let's see, we have basically dx squared plus dy squared, square root. Okay, well, this is our arc length formula. And so if I pull this out here, this is arc length. And so if I want to go ahead and pull out a dx, I'm going to have negative x star to x star of square root of 1 plus dy over dx squared, and then I've pulled out the dx there, okay? And so this is probably the arc length formula that you're more familiar with, and this is the derivation using just a local version of arc length where we have like a ds. Here's dx and here's dy. And so we've simply integrated the arc length as the square root of dx squared plus dy squared, and then factoring out a dx, we get the formula that people are more familiar with. Okay, and so if our parabola, if we want to start with alpha x squared minus 1 as our y, then let's go ahead and take the derivative with respect to x here. And it's just going to be 2 alpha, right? So we get integral from negative x star to x star of square root of 1 plus 2 alpha x, right? 2 alpha x squared dx. Okay, but here's the problem. Okay, so this looks okay. I mean, it's not really a nice integral, but it doesn't look horrible, right? The problem is these bounds. Okay, these bounds are gross. All right. And notice how they're not really fixed. They actually explicitly depend on alpha here, okay? Because as I change alpha, I'm squeezing the parabola, and so my x stars are going to change, okay? So it turns out I have some function of alpha here in my bounds. And now, all of a sudden, my integral is really gross. And if you want to continue moving forward, trying to solve the problem this way, you can. You're going to run into a brick wall, or at least I ran into a brick wall. Maybe you can do it better than I could, but the reason is that we can't really disentangle the points of intersection with the circle from the actual integrand itself. And so because the bounds of integration are kind of entangled with the parabola itself, then it makes it much more difficult to integrate explicitly. And so this is just kind of a mess here. And I knowing as to whether or not this is 4 is basically impossible. Okay, so I was working on this problem and I was kind of stumped and kind of hit a brick wall of like, I don't know how to integrate this. I've tried quite a few different ways. And then I just kind of decided to take a break from the problem and went and walked over to go get like lunch. And as I was walking over to get lunch, I started thinking about, what are some other ways to attack this problem? What are some other ways to set up this integral to make it solvable? And there's something I realized is that essentially these bounds of integration, right now they're not. We can force them to. We can have more control over them than we're trying here, because of the fact that we're fixing this vertex to be -1 actually causes us to lose a ton of control. All right. And so if I actually change the vertex, if I can shift that vertex a little bit to get more knowledge of the x star of the intersection with the circle, it would be a very good thing. And so this idea popped into my head of like, what if we just started with a circle here? Okay. And we have our parabola. And let's say we start with a horizontal line. So instead of alpha x squared minus 1, we're just going to do like alpha x squared plus b. Okay. And I'm going to start out with just alpha and b both equal to 0. And so I just get a horizontal line x equals 0. Obviously, arc length is 2 inscribed within the circle here. And now what I'm going to do is I'm going to start increasing alpha. And so once I increase alpha, the parabola is going to lift itself up, and I'm going to get something like this. Okay. And now I want to kind of determine these points of intersection. And the way I'm going to do that is as I increase alpha, I'm going to simultaneously shift b. So such that, in fact, I'm going to balance the parabola with respect to the center of the circle so that the height of these intersection points with the circle is precisely equal to the vertical shift of b. And I can shift b as much as I want. So I'm going to increase alpha. Every time I increase alpha, these intersection points are going to change. And then I'm essentially just going to vertically shift B such that whatever, say they shift by, I increase alpha by whatever, some infinitesimal amount, and then say the points of intersection shift by some dy. Well, then I'm essentially just going to shift B to half of that increment to kind of balance that equally above and below the center of the circle. And so what I'm going to restrict, I'm essentially going to add a restraint to this parabola that the vertex B is precisely going to be equal to the points of intersection. Okay. And so quickly we can calculate the points of intersection. Okay. So the points of intersection, we have the circle, which is governed by x squared plus y squared is equal to 1. Right. And then the parabola is governed by alpha x squared, y is equal to alpha x squared plus b. All right. And so there's an intersection point precisely when we can just plug in x squared here. And so we're going to get y is equal to alpha times 1 minus y squared plus b. And so we're going to get that, let me think about this. Okay, so let's start with the circle. And now I'm going to, instead of just having alpha squared minus 1, I'm going to have alpha x squared minus b, where b is just going to be some vertical shift that I'm going to determine later, okay? And now, at first, I'm going to let alpha and b both be 0 initially, okay? So I'm going to start with a horizontal line here through the circle. And clearly the arc length inscribed in this circle is just 2. And now I'm going to start increasing alpha, okay? And so when I start increasing alpha, what's going to happen is the parabola is going to get lifted upwards. And all of a sudden, I'm going to get these points of intersection with the circle that are non-trivial, okay? And so what I'm going to do is I'm going to set this b such that it shifts the parabola down in precisely a way that the points of intersection are equal to this vertical shift b, okay? So it's kind of a non-trivial thing, but I'm essentially like creating a shift in alpha that's also simultaneously changing b in a way that the parabola is kind of like balanced around the center of the circle, and the points of intersection with the circle are the exact height of the vertical downward shift of the parabola. Okay, and so mathematically, what I need to do here is I essentially need to figure out that if I have the equation x squared plus y squared is equal to 1 for the circle, and then I have y is equal to alpha x squared minus b, what I'm going to do is I'm going to solve for the points of intersection first. And so I'm going to set x squared equal to 1 minus y squared. So I have y is equal to alpha times 1 minus y squared minus b. And now I'm going to add this restraint that when I evaluate this equation at the point of intersection of the circle, okay, then I'm going to necessitate that point of intersection has a height of b, okay, corresponding to this idea that I've just described of kind of shifting the parabola in such a way that we gain more information about the points of intersection by adding a restraint to that vertical shift in the vertex, okay? And so when I restrain y star to equal b, I'm just going to go ahead and plug that into this equation, and I'm going to get b is equal to alpha 1 minus b squared minus b here. And so I can solve for b now, okay? And it's just a quadratic equation. So I'm going to have 2 over alpha b is equal to 1 minus b squared, I think, right? 2b, yeah. So b squared minus 2 over alpha b b squared plus 2 over alpha b minus 1 is equal to 0. And so b is equal to negative 2 over alpha plus or minus plus 2. All right, and quickly I can observe that that I want b to be positive, because remember I have alpha x squared minus b, and so this is a positive downward shift in the parabola. If I were shifting the parabola upward, it would be totally inefficient, and that would be nonsensical. So that means that I need to take the positive root of this equation here. So I'm going to take the positive root, and now I'm just going to simplify algebraically. So I'm going to have negative 1 over alpha plus square root of 1 over alpha squared plus 1. And this is equal to negative, or I'm just going to simplify it outright. So 1 plus alpha squared square root minus 1 all over alpha. Okay. And so this is our b. This ends up being our b. And as you can see, it's kind of interesting because what we've done is we're no longer just shifting alpha like the coefficient of the x squared. We're like shifting the coefficient and the vertical shift in like in a coupled way. And what it does is it's so beautiful because it gets rid of the coupling in the integral, and it makes the arc length integral actually possible to compute. Okay, so let's go back to our equation here. We have alpha x squared minus b, and so this is still now alpha x squared plus 1 minus square root of 1 plus alpha squared over alpha. Okay. The important piece of this, and the crucial element that makes this such a beautiful method, is that when I set up the arc length integral, okay, integral from x star, negative x star to x star, I still just have a square root of 1 plus y prime squared dx. And this y prime, this dy over dx, remains unchanged, okay? Because b is just a constant shift. So the derivative of y with respect to x is still just the clean 2 alpha x. And so this is still going to end up being a 4 alpha squared x squared, okay? Which is really, really nice, because all of this gross like analysis that we did changing the b value didn't change the arc length integral at all, okay? And so now the last thing I need to do is just solve for the bounds of this integral, okay? And so the bounds are specifically the intersection with the x, and this is actually not too difficult to do because I know that y star is equal to b, right? I've restricted the point of intersection with the circle to be b, and so I know that that x star is just going to be the square root of 1 minus y squared, okay? Because it's on the circle, okay? So because it's on the circle, I can immediately solve for x star given y star. And so I know that x star is just the square root of 1 minus b squared. And now I can plug in my value for b, okay? And it is going to be kind of gross, okay? But the point is that essentially we have an integral that's entirely these bounds are now like much more fixed, okay? So we can solve this integral explicitly in terms of alpha and x, okay? And it turns out that it's still a really, really gross integral, okay? But the crucial step is going to come in. Let me show you all how to like finish off the problem. So instead of like finding a specific example where the arc length is like greater than 4, which is just like a gross way to solve it, all you need to do is to prove that if I take the partial of s with respect to alpha, okay, this approaches a negative number. So if I take the limit as alpha approaches infinity, this is strictly less than 0, okay? And then the second thing I need to show is that the limit as alpha approaches infinity of just the arc length is equal to 4, okay? And so if I show these two things simultaneously, then I essentially show that in the limiting case, as we squish this parabola closer and closer to just like two vertical lines, then indeed the arc length does approach 4, okay? And this is kind of a really gross thing to do using calculus, but it actually does work out. And then this limit, we just need to show that partial s over partial alpha, limit as alpha approaches 0, approaches infinity, is negative. So that means that we're approaching this limiting case where the arc length is 4, but that's actually an inefficient case. So as we get infinitesimally close to that case, we're eventually going to have to hit a value that's greater than 4, simply because we're going to decrease to this limiting case of the arc length being 4. And so it's the case where the parabola is just two vertical lines, two diameters of the circle, is actually inefficient because of this first condition. Okay, and I'm not going to go through the actual integration step here because like it's just a bunch of gross calculus and like integral tables and everything. But the point is, the key point is that the integral becomes possible because of this clever little trick, this clever idea of letting the vertical shift in the parabola be equal to the height of the intersection point. Okay, and without that, the integral is literally impossible. Simply because this equation for the bounds is just too gross to figure out. It's too entangled. Okay, and so by setting this restraint on B, we're able to solve for these bounds explicitly in terms of alpha, okay? And once we can solve for them explicitly in terms of alpha, then we can use brute force computation to like solve this integral. Using integral tables, etc., we can just use brute force computation and prove these two conditions, okay? That basically ensure that indeed it is possible to fit a parabola of arc length greater than 4 inside a circle of radius 1. Okay, so I hope that helped, and I hope you're not disappointed that I didn't actually go through these two conditions. You know, it took me like 30-45 minutes to actually prove them explicitly, but honestly, you should try it yourself, knowing this key idea of how to set up the problem. You should try to arrive at the same conclusions that I did, okay? And the point that I'm making here is that sometimes in math, you can do all the computations in the world and you're not going to break through, right? So like if you try to do this original method that I was showing you, you could try to compute this for like 4 days straight. And I think it's very unlikely that you'll actually get anywhere because the integral is just too gross. It's like, it's not doable. However, if you're able to find some clever trick or some clever idea that gives you more control over the problem, that's how you're able to break it down into something that you can solve. And so the key point is that when I set this additional restraint on the vertex of the parabola to give me more knowledge about the points of intersection, or like restrain the points of intersection, it didn't actually change the formula for the arc length, because the formula for the arc length only depended on partial y over partial x, right? And so because it's invariant with respect to that vertical shift, then the arc length, the integrand itself doesn't get any grosser, but the bounds are much, much nicer to work with. Okay. And the last thing I should note is that as we take alpha to go to infinity, okay, then essentially the points, as alpha is going to infinity, then the points of intersection are approaching here, okay? And so because of this restraint, our vertex is indeed going to approach the base of the circle. And so in the limiting case, we actually do have the vertex of the parabola at the bottom of the circle, okay? And we haven't fixed it there, but that is still our limiting case. And so this still technically builds on the original kind of intuition, the original idea of how to solve the problem. But it just changes things slightly to give us more control. And so, yeah, I hope that helped. And I hope that you go through this problem and try to, arrive at the same conclusions that I did. I think it's a really great computational exercise, um, knowing this idea. So, anyways, hope you all are having a great new year. Happy January 1st. Happy 2023. And hopefully this will be a great year for math, physics, and everything else in life. So, all right. Until next time.